Right, so this booklet is all on forces, energy and power. So what it does is it actually, we take the National 5 stuff and we just expand on it a little bit. So there's not really much new stuff in it. There's just more expansion of the old stuff. Okay, so you'll be familiar with all of these equations, hopefully. F equals ma, W equals mg, Newton's laws, and your energy equations that you came across a couple of years ago. Okay, so just a reminder about Newton's laws. Newton's first law. So when two forces are of equal size and opposite in direction, act on an object, the forces are balanced. And we know that if the forces are balanced, then something can either be stationary or moving at a constant speed. Okay, that's the main one. So, for example, this one's got 4 newtons in that direction, 4 newtons in that direction, and the effect on the object is just as if there is no force at all acting on the object. Another way to describe this is to say that resultant force is 0. So Newton's first law, and this is Newton's first law, so you might need to say what is Newton's first law. An object will remain at rest or continue to travel at constant speed in a straight line unless acted upon by an unbalanced force. In other words, guys, if balanced forces are acted on an object, it's either going to be stationary or moving at a constant speed. So examples, a car travelling at constant speed. If it's at constant speed, the force of the engine is balanced by the air resistance and friction in the opposite direction. And spacecraft moving in deep space. In the vacuum of space, there's no air resistance to oppose the motion of a spacecraft. Once the vehicle is moving, its engines can be switched off, since the vehicle will continue to move at a constant speed in a straight line. There's also the example of when somebody's standing on a bus or a train and the vehicle starts to move. The passenger will appear to fall backwards. Their body is obeying Newton's first law by remaining at rest, but their feet are dragged forward because there's friction between the floor and their feet. And the seat belts example, so if you're driving in a car and you're in the car and it's driving at a certain speed, then you will continue. If the car brakes, if you have nothing to stop you, the brakes are only on the car. If there's nothing to stop you, then you will continue to move at that constant speed out of the windscreen. Okay, so seat belts are there to apply that braking force onto you as well, and that means you don't end up flying through the windscreen or into the passenger seats. And the tendency of an object to remain at rest or to continue its motion at a constant speed is called inertia. So Newton's first law, whirlwind, basically balanced forces equals constant speed or stationary. Newton's second law introduces unbalanced forces. So if you've got a force in one direction and a force in the other direction, they're not equal and opposites, then you've got unbalanced force. So in this case, we've got 10 newtons in that direction, 4 newtons in that direction. Therefore, the overall unbalanced force would be 6 newtons in that direction. Okay, so forces are not balanced. The object will neither be stationary nor moving at a constant speed in a straight line. There's an unbalanced force of 6 newtons to the right in the diagram above. The unbalanced force causes the object to change its speed. And unbalanced forces cause objects to accelerate. And Newton's second law states that if an unbalanced force acts on an object, the object will accelerate in the direction of the unbalanced force, so in the direction of the biggest force. And the acceleration of the object depends on 2 factors. What are they? The force, the outside of the force, and mass. Yeah. So that's acceleration, well, it's proportional to force, but inversely proportional to mass. So if you increase the force, if you push it harder, it will accelerate, the acceleration will be bigger. But if you increase the mass, if you push something heavier, the acceleration with the same force as you push something lighter, the acceleration will be smaller for the heavier one. And you can investigate that using the equipment where you have a double mask and a light gate, and you get a string. You all did this last year, hopefully. And a string attached to a pulley with masses on, and the masses, when you drop masses, they cause the force, the unbalanced force. And the light gate measures the acceleration because the first mass is the initial speed, the second mass is the final speed, and it also measures the time it takes for from one mass to the next mass. So that gives you the acceleration. Okay. And you can change the masses here to change the unbalanced force, or you could change the mass of the actual trolley here to change the mass of the trolley. Okay. Yeah, I'm just stretching. So, if we're going to investigate the effects of forces on a body, then it's necessary to get rid of friction. So this is quite good if you end up doing your assignment or anything like that, where there's ramps involved. Quite a good evaluation point. This can be done by two main methods. First is to reduce it as much as possible by using something like a linear air track or well lubricated wheels on a vehicle. The second is to use a friction compensated slope. On a friction compensated slope, the frictional force is balanced by a component of the force of gravity. We'll do a little bit more about the components of force of gravity later in this book, actually. A known unbalanced force, the weight of the falling masses is applied to a known mass, the mass of the trolley, and the resulting acceleration is measured. And the results for that, you do two experiments. One of them you change the force, you keep the mass constant, and one of them you change the mass and keep the force constant. So you end up with a straight line through the origin with acceleration versus force, showing that acceleration is proportional to force. And if you plot acceleration versus 1 over mass, you also get a straight line through the origin, showing that acceleration is proportional to 1 over mass. So combining those two proportionalities, we get acceleration is proportional to force over mass. So rearranging that, you get force is proportional to mass times acceleration. And with proportionality, you can rewrite proportional to as is equal to a constant times by those values. So force is equal to a constant, k, times by mass times acceleration, and luckily in this case k is 1, so we can ignore it. So as a result, 1 Newton is the force that would give a mass of 1 kilogram and acceleration of 1 meter per second per second. And we end up with the equation, which is Newton's second law. Force is mass times acceleration. When force is in newtons, mass is in kilograms, acceleration is in meters per second squared, meters per second per second. And some examples of that: vehicles where an engine provides an unbalanced force, objects falling under the force of gravity. Okay, we're going to do some worked examples later in this booklet, but again, you've done lots of these in National 5. So that's Newton's second law. Newton's first law is balanced forces, constant speed or stationary. Unbalanced. Newton's second law is unbalanced force equals mass times acceleration. And Newton's third law is every action there is an equal but opposite reaction. So if A pushes on B, B pushes back on A with the same force. Okay. So, for example, rockets and jets. So the action, the vehicle pushes hot gases backwards. The reaction, the hot gases push the vehicle forwards. So in terms of the water rocket, the water will go down. So the rocket will push water down and the water will push the rocket up. And also if you let air escape from a balloon, balloon pushes the air to the right and the air pushes the balloon to the left. And quite often astronauts use the same kind of thing with air guns to move themselves around. So each object exerts an equal sized force on the other object involved in the interaction. And this means that the forces must be in exactly opposite directions. So if A exerts a force on B, B exerts an equal but opposite force on A. It's not always intuitive because it's quite often you think, well, if I'm standing on the floor, I'm exerting a force on the floor, but also the force is exerting an equal force up on me. And it's not the most intuitive thing to think about because you don't feel that force, but you don't fall through the floor, so it must be there. Right, I want to do a couple of examples, then if it stops raining, we'll go out with the water rocket, then we'll come back in and do some more examples. Is it raining at the moment? Well, we've still got a few examples to go through. Right. Okay. So the force of gravity, because that's what we're going to be looking at with the water rocket. I have to shoehorn it in somehow. The force of gravity, or the gravitational force acting on an object, is called the what of the object? Yes, thank you, the weight of an object. So there's a free body diagram, yes, still revision. A free body diagram is just a block with an arrow on it or a circle with an arrow on it. So weight is given the symbol W. Remember, if you are drawing any diagrams like this, or it asks you to draw diagrams in exams or anything like that, never write gravity to be the force down because it's not weight. The force down is the weight. The weight is the force due to gravity. So weight is given the symbol W, and the unit of measurement of weight is the Newton. And the weight of a particular object depends on where it is measured. So it's much smaller on the moon than the Earth because the moon is smaller than the Earth. And we will actually talk about more about that in a couple of booklets' time because we talk about how we actually calculate gravitational field strength using the masses of the planets or whatever they were on. So because the moon is smaller than the Earth, gravitational pull is weaker. In deep space, where the force of gravity is negligible, the weight of the object is also negligible. So it's very rare that you actually get that situation where you're in deep space and you're next to there's nothing around you at all, because obviously every single thing, every person in this classroom does have its own gravitational field strength, but it's just tiny compared to the Earth. But if you are next to absolutely nothing, then that is where your weight becomes negligible because there's no gravitational field strength around you. So W equals mg. So when an object is dropped, it's acted upon by the force of gravity. We all know that because we've been doing a lot of that with our Suvat equations. The force pulling the object down is the weight of the object. So example 1, nice easy one. Objects of mass 5 kilograms and 100 kilograms are dropped near the surface of the Earth. Ignoring the effect of air resistance, calculate the acceleration of each object. So we've got two objects, 5 kilograms and 100 kilograms. Okay, so to find the acceleration, we need to do F equals ma. So we need to know the force, the unbalanced force downwards. Okay, so the unbalanced force obviously would be the weight. So mg. So for the 5 kilograms, it would be 5 times 9.8, which is 49 newtons. And for the 100 kilograms, it would be 100 times 9.8, which is 980 newtons. So to find the acceleration of the object, and I know most of you will already know what the acceleration is, but just to go through the motions and prove it. Unbalanced force is we don't have a force upwards, so the unbalanced force is just the weight. So the acceleration is, of course, 9.8 meters per second squared for both of them. So the acceleration due to gravity is equal in magnitude to the gravitational field strength. If you've got it written down, you can have a read through the next example. What do you mean, is it a typo?
How much fuel is used by the rocket?
Yeah, so basically you want to, how much does the mass change? So basically how many kilograms of fuel is used. Okay, am I good to move on? Okay, right, example 2. A firework rocket of mass 2.5 kilograms is launched vertically upwards from the surface of the Earth. Its motor exerts a thrust of 95 newtons, so we've got 95 newtons up. Ignoring the effects of air resistance, calculate the acceleration of the rocket. So I always draw a diagram. My rockets are terrible, notoriously terrible. So it's 2.5 kilograms. Got a thrust upward of 95 newtons, and our downward force will be the weight of the rocket. So 2.5 times 9.8, which is 24.5 newtons. Okay, so hopefully we all remember how to do F equals ma when we've got two opposing forces. So it's the unbalanced force so it would be 95 take away 24.5 is the mass times by the acceleration. So the acceleration would be 95 take away 24.5 divided by 2.5, which should come to 28.2 meters per second squared. It's positive and that makes sense with the question. It's got a bigger upward force than downward force, so it will be accelerating upwards. Okay, have a read through example 3 if you've got that written down.
She just leaving the zero gravitational field strength in outer space.
Is anyone still writing this? You still writing? That's okay. Example 3 is a tricky one because there's a lot going on in it. Okay, am I okay to move on? Shout now if you don't want me to. Okay. Right, example 3. There's the back. Are we okay? Thank you. Right, the graph shows how the acceleration of a rocket in outer space changes during a 10-second period. The rocket motors produce a constant thrust of 4 times 10 to the 3 newtons. So when it says in outer space, that means, as Nicholas said, we're assuming that the gravitational field strength is 0. Okay, so we've got a rocket, and it's got a constant thrust of 4 times 10 to the 3 newtons, and its weight will be the mass times gravitational field strength, but gravitational field strength is 0, so it's not got any backwards force on it. Okay, when it says how much fuel was used by the rockets, what it's meaning is how much mass of fuel was used. So we need to find out what the mass has changed, how the mass has changed in those 10 seconds. Okay. So what we need to do is we need to look at the start, and we need to look at the end. We need to find the mass at the start and the mass at the end. Okay, and then take them away from each other. So at t equals 0, so at the start, we'll use F equals ma, because we know the force, unbalanced force, is 4 times 10 to the 3. And we know the acceleration from the graph is going to be 20 meters per second squared. So 4 times 10 to the 3 is the mass times by 20. So that's 4,000 divided by 20 to 200 kilograms. And then at the 10 seconds, so t equals 10 seconds, we do the same. The force hasn't changed, so it's still 4 times 10 to the 3. And the acceleration at 10 seconds is increased to 100. So that'll be 40 kilograms. So you'd need a sentence at the end just to say the mass of fuel used is 200 take away 40, so 160 kilograms. Just in time for the sun to come out. Hopefully it'll stay out. Right. So, what did you do on paper and we'll probably come back to this more about the and you fill that one maybe only like half